that. Yes, Mariam and Aisha.
mu naught I by 2 pi.
Mu naught I by 2 pi. Correct. So this distance is A, right? And the current is flowing like this. So when we talk about the direction, we put our, right. So, okay, when we talk about the direction, so this is going inward, right? So we put our fingers, our thumb in the direction of the current. So then we get the direction of magnetic field. So magnetic field was inwards, right? And then we calculated the magnetic field due to semi-infinite wire, right? So this was how much, Aisha and Mario?
mu naught I by
Yeah, 4 pi A, right, guys? So then then we learned about the magnetic field due to circular wire. What? Where? Circular wire at center. Right. So this was how much? Yes, Saad and Aisha and Maria. Yes, guys.
You know, I like to
Mu naught I by 2R. Right. Good. So you guys, yeah. Okay. And then we calculated the semicircular wire. Right. Semicircular wire. So this was B, which is mu naught I by 4R. And then we calculated for different angle also, for some angle alpha, right? So these were the different distribution. And then lastly, we calculated the magnetic field at axis of a circular wire, right? So if this is the magnetic field and the current is flowing like so the current is flowing like this, right? So it is going in this direction. Right? So then we calculated, or let me write this direction. So this one, and the current is going like this. So then we found out that axial line, the magnetic field will be in this direction, right? And this is R, and this is from this point we are calculating. So this is X, and this is some distance R, right? So then we found out that, oh, so not in this direction, but it is going right. So in this direction. Okay. So then we found out that the magnetic field is in this direction, and its magnitude is what? This is B, which is mu naught I by what? So what was the magnetic field, guys? Do you remember? Yes.
you know, I R square by 2 R square plus X square whole 3 is to 2.
Yes, good. And it was directed in this direction, right? So we use the Maxwell thumb rule. So if this is in this direction, so magnetic field is in this direction, but it is coming out of, right? So it is coming out of this circular loop. So the magnetic field will be in the left direction, right? So let me again show the direction, that if it is going in this way, so this is left, right? And if it is coming out, so coming out of the screen, so coming out of the screen, then it is right, right? So we extensively talked about the direction. Okay, so this is what we have done so far, and then we talked about the magnetic, and then we talked about the Ampere circuital right? Ampere's law. So what did so this is just an extension of Biot-Savart's law. So this is an extension of Biot-Savart's law from which we can easily, using the geometry, we can easily calculate the magnetic field of certain materials or certain charge carrying wires, current carrying wires. Okay. So, but it is difficult for this Ampere circular law, using the Ampere circular law, to calculate for the circular wire. So it is difficult to calculate for the circular. Okay. We can calculate for the long straight wires. We can calculate for the solenoid. We can calculate for the toroid. We can calculate for the thick wires, but we cannot calculate for the circular wire. Okay. Yeah. So what is this Ampere circuited law? It says that if we have the current which is flowing like this, right? So what we do is that we make an Amperean loop, right? And if this is in this direction, so this would be in this direction, so that the current is in the upward direction, right? So this is called the Amperian loop. Okay. And what is the characteristic of this Amperian? So characteristic. But before we do that, what is the Ampere circuit law? So it says that when we take the closed, right, and this is the line integral of magnetic field. So this will give us the mu naught times the current in. So this is what we call the Ampere circuit law, right? And can you guys tell me? So you guys have heard about the Gauss law, right? So what was the Gauss law? What was the Gauss law? Yeah. So Saad, you were also there. So this is the question for all three of you guys. What is a Gauss law for electric? Yes, guys. For electric charge, what is the Gauss
Sigma by sine.
law? So you guys remember this, but you guys have so Q enclosed by epsilon. This is the Gauss law, right? Now you guys remember. So do you guys remember now? Right. So in this case, we see that this is very analogical to this one. But the difference is that we are taking the closed line integral in here. But this is a closed surface integral. And this is a line integral. Okay. So this is a closed surface and this is an open surface. Open surface. Okay. And this is a closed surface. This is an open surface but closed line. Closed line. Right. And this is a closed surface. Okay, so this is only the difference between the Ampere circuital law and the Gauss's law. And they are analytical. So you can see the analogy from here. P is E and then line integral changes to surface. And this is mu naught times, this is 1 by epsilon naught times. Understood? Okay. So then what are the characteristic of Amperian. So remember that this line integral is enclosed by the Amperian loop. right? So line closed line integral of magnetic field in the Amperian loop is equal to mu naught times the uh, uh, current enclosed by the amp. Okay, so this is what we call the Ampere circuit law. So what are the characteristic of this Amperian? Right. First is that B is perpendicular to the line element, or second is that B is parallel to the line element, or third one is that B is 0 in the. So these are the three conditions that we follow in applying an Amperian. Okay. So up to this point, is it clear, guys? Any doubt up to this point? Yes, guys. Any doubt up to this point?
No, sir.
Okay. So you guys note down this part. Okay, you guys note down this part, and then we'll see how to use this Ampere circuit. So you guys please note down this. And whenever you guys want me to scroll down the screen, you guys tell. So for the infinite wire, right? I didn't derive from the Ampere from the Biot-Savart's law. I didn't derive the magnetic field using the Biot-Savart's law for the infinite wire. Because that was a difficult task. But you guys will see that how using the Ampere circuit law, we can easily calculate the magnetic field for infinite wire. So note it up to this point, guys. Yes. Guys, noted.
No, sir.
Please quickly note down this part and then tell me when you guys have noted it down. So Aisha school is reopening on 28th. Mariam school is also
21st.
21st.
Yes, sir.
Oh, sorry. And Mariam, your school? Yes,
So
Mariam,
mine is also 21st.
21st. And Saad, what about you? Yes, Saad. When is your school reopening? Yeah, did I not write pad that? So, where is yes, Saad. What about your school? Where is Saad? Oh, Saad is here. Okay, so noted, guys. Yes, noted. Guys, did you guys note it down? Aisha, Saad, and Maryam. Hello? Hello? Am I audible, guys?
Yes.
Oh, yes. So then please let us move on to the next part, which is magnetic field of a long, long wire. So you guys can see that how we can use the. So this is a very long wire, and the current is flowing like right. So when we put our thumb in the direction of the current, so this will be the direction of the magnetic field. So in here it is inside and in here it is outside. So this is what we take the Ampere. So we take an Ampere loop at some distance. Let's say we are calculating the magnetic field at this point. So let's say at okay. So the Ampere circuital law says that the integral B dot dl, right? This is equal to mu enclosed, mu naught I enclosed, right? This is what Ampere circuital law says, right? So you guys can see that this magnetic field is in here. This is parallel to the dl length element. So length element is here, right? And the magnetic field is also in here, right? Inside. Understood? So inside I should write as this one. I should write as this one. Okay. So cross. Now both are parallel, so I can write this as PDL and enclosed, and this is mu I, right? And this B is uniform, so I can take it outside. So this is DL and this is mu. And what is the current enclosed? What is the current enclosed, guys? Inside, so this is the Amperian loop. Okay, this is the Amperian loop. So what is the current inside this Amperian loop? This is I, right? So this would be I. And we are integrating the whole dl. So it will make a full circle, right? So what would be this length? Aisha and Mariam Saad, what would be this total length? If I integrate this dl, so this is dl. If I integrate this dl, so what would I get? I'll get the total length, right? What is the total length? Yes, Aisha, Mariam, and Saad. What is the total length? If I integrate dl, yes. Yes, guys, you can write in the chat box if you don't want to vocally answer. Don't think about the right and wrong answer, right? So, yeah. So, 2 pi r. Right. So, Mariam is saying that if I integrate whole length, so I will get the radius is d. So, Mariam is saying that 2 pi a I will get. Okay. So Aisha and Saad, what are you guys saying? Is this correct? Yes, Aisha and Saad.
Oh, yes, sir.
Yeah. So you said okay. Yeah,
Yes,
Aisha.
sir.
Okay. So Aisha is also saying that this is 2 pi a. Saad, do you agree? Yes, Saad, do you agree with this? I guess there is a problem with Saad's mind. Okay, yeah. So Saad is also saying it is 2 pi. So this is B 2 pi A and this is mu naught I. So I will get my magnetic field as mu naught I by 2 pi. So is this matching with the answer that we know? Yes, guys, is this matching with the answer that we know?
Yes, sir.
Okay, so this is we can see that how using the Ampere circuital law we can easily calculate the magnetic field of long wire. Okay, so you guys please note it down, and then we'll calculate the magnetic field for the thick wire. So quickly note it down, and then direction part you guys already. So direction we can calculate from the uh, Maxwell's right hand thumb. So please, yeah. And whenever you guys have noted it down, please tell. Noted, guys. Noted, everyone.
Done, sir.
Okay. So now let us move on to the magnetic field due to a thick wire. Okay, so we have a wire like right, and we want to calculate the. So we have two regions. Okay, this is inside. So current is passing. So the current which is passing in this region is so some current is oh, it's not showing. Some current is is I. Right, total current is I. So current is passing in this direction, which is I. Total current. Okay. Now we want to calculate the magnetic field at this point. Okay, magnetic field at this point, or we want to calculate the magnetic field at this point. This is outside and this is inside. Okay, so let us calculate the magnetic field. First is case first. magnetic field inside. Okay, so let us draw the Amperian loop, right? And the radius of this, so the current is flowing in this right in this thick wire. So it has some area of cross section, right? So what is the area of what is the shape of the area of cross section? You can see that this is a circle, right? So this is a circle. So if I cut this wire, so I will get a cross section which is a circle. Okay, so that radius is yeah. So that radius is from center. That radius is r, or let me write it as a. So it has area of cross section which is a circle, and then it has some radius which is a. And I am calculating the magnetic field at this point. Okay, so I am calculating the magnetic field at let's say this. So I will make an Amperian loop in here. Okay, and the current is flowing in this direction, right? So this is this direction and this is this direction. Okay, and if I am calculating the current outside, so in here this would be I will make an Amperian loop would be which would be this one. Okay, and in here the current is flowing in this way. The magnetic field is this way and this. In here it is this way. So this is my Amperian loop. So I have this distance is r, and this distance is also a small r. Okay, so this is outside and this is the inside. So let us calculate for the outside one, right? Outside one is simple one, so let us calculate first the outside one. So you guys already know, using the Ampere circuited law, E dot ds, this would be mu naught I enclosed, right? So we have this big Amperian loop. This is the Amperian loop, and then this one is the Amperian. So this again, this is say V dot dl. This is VDL and mu naught. And for this big one, what is the total current which is passing? For this big Amperian loop, what is the total current which is passing? For the bigger one, right? For the bigger one, what is the total current which is passing? So this is my current carrying wire, right? And I am calculating the magnetic field in this region. So the Amperian loop is covering all this region, right? So in this region, total current is passing through this I enclosed is this current, right? Correct, guys? So how much would be the current I enclosed? Yes. Any guesses? Any guess that you guys want to make for the bigger loop? Yes. Okay. So if I write I, is this correct? Yeah. Did you guys understand this part?
Okay, explain again.
Yeah. So you see that for this bigger one, for this bigger Amperian loop, right? For the bigger Amperian loop, for this one, total current is passing through this section is I, right? So whole I is passing through this Amperian loop. Understood? Is that clear? So we have this region and total current, this total current is passing through this region, right? Because we have this region. Understood? So let's say that I have okay. So I have an Amperian loop. One minute. So yeah, I have this Amperian loop. Okay. So this is not in shape of a circle. So I have this Amperian, and this current is passing, right? So this whole current is passing through this Amperian loop. Correct? Understood?
Yes, sir.
Yeah. So the big for the bigger one, right? For the bigger one, the total ion closed is I. Understood? So when I integrate this dl, okay, and remember that this is r, this is r. So when I integrate this, so b is taken outside. When I integrate this r, so what would be this? What would be this? dl. If I integrate this dl, what should be this? What should be this length, closed length? That would be the perimeter, right? Radius is r and the perimeter that it is making. So this would be 2 pi, yes, 2 pi r. Yes, correct. Right. Yeah, sure. So then I get the magnetic field as mu naught I by 2 pi r. Understood? Is this clear, guys?
Yes, sir.
So the outside magnetic field, it is varying like 1 over r. Okay. Now let us, before we talk about the inside, so you see that we have this thick wire, right? And in the whole region, the total current is passing, which is what? I. Okay. So this is the whole region, meaning that this surface, total surface, right? So this total surface, this side is, so this radius is A. Okay. This is not, let me choose the other one. So this radius is A. Okay. And in the pi a square region, in the whole region, the current is passing I. Am I clear? Is this clear, guys?
Yes, sir.
Okay. So then if I want to calculate the current passing through this region, right? So then I'll have to take the surface in which it is passing. So this is what? This is pi and r square. Is this clear, guys? Is this clear? So this
Yes, sir.
region, this surface is pi r square. So if I calculate in unit area, this would be I by pi a square. And in pi r square area, this would be I by pi a square into pi r square. So this is I r square by a square. Is this part clear to you guys? So if I am calculating the current passing through this area, if I am calculating the current passing through this area, so this would not be I. It would be less, which is this one. Understood? Clear? Aisha, Mariam, and Saad, is this clear?
Yes.
Okay, so now we can calculate the magnetic field which is inside. So the second case is B inside. right? So we have this thick wire and we are taking the Amperian loop in here at this r distance. Okay, and this radius is a. So V inside, for V inside again using the Ampere circuital law. So this is mu naught I enclosed, right? So again this is B, right? Both are parallel, so BDL mu I enclosed, and then B is taken outside DL. This is mu, and I enclosed we have calculated. So this is I r square by a square. So this is B and 2 pi r, and this is oh. So, sir, are these previous recorded? I would like to watch it. Yes, sir, they are all recorded. So, yeah, I will ask the Learnivio team to send the links to. Okay, sir. Yeah, so I will send the links. Yes. So this is 2 pi r, and then this is mu I r square by a square. No need to thank me. So this is my job, right? Okay. So 2 pi r and then a square. So this cancels, and we have magnetic field which is mu naught I r divided by 2 pi a square. Okay. So you guys can see that this mu naught I 2 pi a square are constant. So magnetic field is varying like r. This is directly proportional. Okay. So this is directly proportional. So if I make the graph B versus R, this is R, this is B, okay. And let's say this is R equal to A. So up to R equal to A, this is inside. So up to R equal to A, it is straight line. And then after A, after A, it is varying like 1 over R, which is hyperbola, right? So this varies like oh, okay. So this is B directly proportional to R, and then this is B, which is inversely proportional to R. Is this part clear to you guys? Is this part clear? Yes, guys.
Yes,
This
sir.
okay. So please note down from here. Yeah, this part you have noted it down. So please note down from. Due to long while you have you guys have noted it down, right?
Yes.
Please, and if you have any doubt, so please don't hesitate to ask. Oh, I have my tea. So in the meanwhile, I will. And this Saturday, I will take an extra class. Okay. So we'll speed up so that we can complete this chapter, right? And in all of your school, the fourth chapter has been completed. So what I want is that uh, uh, so on till Saturday, right? I want to complete. Oh, so we have only one day. Yeah. So in the next week, I want to complete this chapter, right? Then four chapters will be completed, and then I will start the revision, right? I'll start the revision, and then we'll do some problems. So in that way, yeah, in that way we can understand it properly. Whenever you guys want me to scroll down the screen, you guys tell Noted, guys.
Now, sir.
Yeah, so please note down this part. Yes, noted, everybody. Should I scroll down the screen?
Yes, sir.
Completed, guys.
Well, sir.
Mariam and Saad, what about you guys? Completed.
Yes, sir.
Okay, so now let us talk about the solenoid. Okay, so we have, right. So what is a solenoid? So it is a, right. It is a circular many turns of coils, right? So it has many circular turns. Okay, and then we can easily calculate the magnetic field using the Ampere circuited law. Okay, so we have this solenoid, right? So these are all circle, and the current is flowing like okay. So how should I? If it is, this is this direction. Okay, so it is coming out. This direction is coming out. Okay, so it is coming out, and then it is going like this. Okay, so this is the direction. And if this is the current, right? So what would be the direction of magnetic field? So this is like this. It is coming out, right? So it is coming out. Okay. So it is going into the screen and coming out. Coming out of this screen, right? So what would be the direction of magnetic field? You guys tell. using the right hand thumb rule, what would be the direction of magnetic field? So if I ask you that I have only one circular loop, so like this, the current is coming out, and in the bottom the current is going down. So what would be the direction of magnetic field? Yes, guys, tell me. What would be the direction of magnetic field?
Sir, can you repeat the question?
Yeah, so I am saying that these are circular turns, right? So in the upper region, the current is coming outside, and in the lower region, the current is going inside. Okay, so in the lower region, the current is going inside, and in the upper region, it is coming outside. Okay, so is this looking outside or inside? Let me draw this. So the current is coming outside. Okay, current is coming outside. So because this is a 2D figure, so we cannot draw the outside. So the current is coming outside. Okay. So you guys tell me that what would be the direction of magnetic field. Did you guys understand the question? So let me say this one. I have this one, and the current is flowing like this. Okay. So and in this one, the current is flowing. This is inside, right? This is outside current, and this is inside. So you guys tell me that what would be the direction of magnetic field. For this loop, you guys can tell, right? So please tell. Yes, Aisha and Maria. We have talked about the direction extensively, right? So for the circular wire, how do we calculate the direction of magnetic field for the circular wire? This is a circular wire, right? And the current is coming outside and then going inside. So what would be the direction of magnetic field? Yes, you guys can tell me any answer. Whether it is correct or incorrect, don't bother about that. I need one answer. Yes. So at least you guys tell me that so we have right hand thumb rule. So do we use the original right hand thumb rule or the alternate right hand thumb? Yes, MO by 2R. Okay,
Alternate, sir.
alternate one. Yes, alternate one, right? So if we use the alternate one, right? So in the alternate one, we place our curved fingers. We place our curved fingers in the direction of the current. So this is the current which is coming outside, right? This is the current which is coming outside. So you guys put your curved fingers in the outward direction. So what is the direction that you are getting? Yes, left or right? What is the direction that you guys are getting? Right. Okay, Mariam is saying right. Aisha and Saad, what about? Oh, Aisha got disconnected. Saad, what about you? What is the direction that you are getting? Yes, Saad. The current is coming outside. Okay, and when you curve your fingers, all the four fingers in the direction of current. So what direction you are getting? Left or right? Mariam is saying right. Okay, what about you? Okay, Saad is saying right. Okay, so Saad also. Yes, Aisha. Yeah, so Mariam and Saad are saying that they are getting the right direction. So for them, this is this one. What about you? Are you agreeing or you have, are you saying left direction?
Right.
Right, right. So you guys know the answer, then why do you guys hesitate? Right. So yes, you guys are correct. The magnetic field is in this direction. For this one, it is also in this direction. For this one, it is also this direction. So magnetic field is flowing like, okay. And the actual figure is this one. Actual figure is this one. And in here, it is going like this one. And then in here, it is going like this one. But we will neglect this one. Okay. So this is so for this short range. For this short range, the magnetic field are parallel. So this is the magnetic, all in the right direction. Absolutely correct. Right. And the total current is flowing is I. Okay. So in this case, what we don't use this circular Amperian loop. For this case, we choose the Ampere loop, which is a rectangle. So we choose this kind of Ampere. This is just above, right? So the magnetic field, this is the magnetic field, right? So uh, this is A, B, C, and the Ampere loop direction is this one. Is this clear? Is this clear? Is
Yes,
this
sir.
okay? So using the Ampere circuital law, B dot dl, right? This would be equal to mu enclosed, mu naught I enclosed. Okay, understood, guys? Is this clear? Okay, so now let's say that this is so this has four lines, right? So we will calculate the magnetic field. So first would be from A to B dot ds plus from B to C B dot ds and plus let's say this is C to D B dot dl and plus D to A B dot dl. This is equal to mu naught I. Is this clear, guys? Yes.
Yes.
Okay. So the current enclosed. So we have total turns, number of turns. This is n. This is the total number of turns, right? So in this way, the current is flowing I. Okay. And for yeah, so okay. And then we have this n turns, right? So this number density in here, this is n. So then I enclosed would be Ni. Okay, where this n is n is total number of turns divided by this length that you are taking AB. So let us take this AB as this is small l. Okay, so from here this is right? In total, the current is flowing I. For n number of turns, the current is flowing I. So in here, the number of turns is this one, small n, right? So for this n, I enclosed would be ni. Is this clear? Is this
Yes,
clear?
sir.
Okay, so this I enclosed is mu naught n, right? And n is so the unit of this is turns per meter. Okay, so this is the I enclosed. Now, can you guys tell me that in this region, in A to B, in A to B, what is the angle between magnetic field and this length element? What is the angle between magnetic field and length element from A to B? Yes, guys. What is the angle between L and B magnetic field? 180.
90.
180. Okay, so L is in this direction, AB is in this direction. Magnetic field is in which direction? So we have this one. So what is this angle?
180.
Okay, and then what is this angle? Hmm? So you have two rays. This one and then again this one is some 30 degree. This one is 90. This one is let's say 120. This one is 180. So if I take this angle and this angle again, so this is 0 degree, right? 0 degree. Yes. So the angle is 0 degree. Understood? So this would be B and integral of dl. Okay, let me not skip these steps. So this is B and dl and cos of 0 degree. Now from B to C. From B to C, what is the angle between B and dl? Yeah, what is the angle between B and dl? dl and B. Yeah, so 90 degree. Yes. Okay, so this is 90. And then in here, do we have any magnetic field? Okay, we'll think about that later, but this is BDL cos of 180, right? And then we have this one D2A, this BDL cos of 90. So cos of 90 0, cos of 90 0. This is, and in here B is 0. So this is also cancelled, right? Because we don't have any magnetic field in this region, right? In C to D, we don't have any magnetic field. So then ultimately we will get B and from A to B, dl, right? This is equal to mu naught N I. So what is the length from A to B? From A to B, what is the length? It is L, right? So, okay, so did I do any mistake? Yeah, so, yeah. So, yeah, then here it would be, this would be N and L, right? Because we want to calculate number of turns up to this point. And the number density is L, so this would be NLI. Okay. So this is NLI, this is NLI, this is LI. This is NLI. So this would be B into L, and we have NLI. So L cancel, and magnetic field is mu naught NI. Okay, is this clear to you guys? Is this
Yes, sir.
clear? So please note it down. Please note it down. And did you guys understand that why this would be NLI? Because number of turns, we want to calculate the number of turns in here, right? So that would be the number density is NL, right? And we want to calculate the number of turns up to this point, through this end, through this length L. So this would be the current would be enclosed would be the number of turns up to L length. So that is L into N and then I. Okay. So that is why we have this NLI. Please write it down, and then yeah, we will do some question on this solenoid. And whenever you guys want me to scroll down the screen, you guys yes. You guys understand this part? Why this
Yes,
would?
sir. Sir,
Because
can you please scroll down? yes, noted everybody. Aisha, Mariam, and Saad, did you guys note it down?
Down, sir.
Done. Saad, what about you?
So let me again clarify this. Let's say you have this one, right? So this is the number of turns per unit length, right? So let's say in 1 meter, in 1 meter we have three turns. All right. So let's say in one very small distance, 1 centimeter. In 1 centimeter we have, let's say, three turns, right? Three turns per centimeter, and we want to calculate at this 4 centimeter length, right? At 4 centimeter, how much would be the current? So at 4 centimeter, the current would be 4 into this three turns per centimeter, and then the current, that is right. So that is why we have this N, L, and R. Okay, number of turns per unit, and then length, and then current. Yeah. So this is the idea, and now let us do one question. So, oh, good one. Yes, Rifa, Assalamu alaikum. You are 10 minutes early. 10, not 13 minutes early. Rifa. Yeah, so the question is that find the magnetic field of a solenoid. Okay, who whose total number, or let me write, whose turns per meter is let's say 70. Okay, and the current which is flowing inside the solenoid is let's say 5 amps. Okay, so you guys calculate the magnetic, and can you guys tell me how much is this mu naught? Yes, how much is this mu naught? Because we know that mu naught by 4 pi. This value we know. This is 10 to the power minus 7. Right. So mu naught would be how much? This would be 4 pi into 10 to the power minus 7. Okay, you guys quickly calculate and tell me what would be the magnetic. Yes, what did you guys get? Are you guys calculating? Yes, so 12.5 into 10 to the power minus 7. So Mariam is getting 12.5 into 10 to the power minus 7 Tesla, right? Okay, Aisha and Saad, what do you guys get? What did you guys get? Aisha and Saad. Yeah, Aisha, you got C. So Aisha got C. Okay, Saad, what about you? So this is simply mu naught n I. All the things are given. So 4 pi 10 to the power minus 7, n is 70. Still doing okay. N is 70 and the current is 5 amp. So this is how much? This is 20, right? This is 20 and 22 by 7 into 70 into 10 to the power minus 7. So this is 10 and this is, oh, okay, yeah, 4, 4, 4 and 10 to the power minus 7. So 4 into pi, 20 and then pi 22 by 7. Okay, so I'm getting this one. 4.4 into 10 to the power minus 4 Tesla. Yeah, so you both are getting this one, right? Which means that, yes, how do you guys calculate? Which formula you guys used? Yes, which formula you guys used? Yeah, you guys check your answer, okay? And check your calculation. So this was one question, and the other question would be that if, yeah, so what is the magnetic field of a solenoid of 500 turns, right? So what is the magnetic field of a solenoid of 500 turns in zero point 0.5 meter length, right? Whose current is whose current is 5 amp. Okay. So now what is given? This is what? This is N or this is N? Which one is this? Which one is this? Yes, guys. This 500 turns is what? Is this small n or capital N? This is capital N, right? So this is given, right? And we want to, because in magnetic field, this is mu naught and Nr, small one. So we have to calculate this small n, right? Which is n by l. Length is zero point 0.5 meter. So n is 500 divided by zero point 0.5, which is 10. So this is what? 100. So this is 1000 turns per meter. Understood? Then we can calculate the magnetic field, which is mu naught. This is 4 pi into 10 to the power minus 7. N is 1000 into I is 5n. Right. So this is 20 into 3.14 into 1000 into 10 to the power minus 7. So this is 28 and 6. Okay. And then this is 1, 2, 3, 4. So 10 to the power minus 3 Tesla. This is the magnetic field. You guys quickly note it down, and then, yeah, on Saturday at 5 p.m. IST. Okay. So 5 p.m. IST, which is 2:30 p.m. KS. So we will have an extra class. Okay. Please note down this problem and be present in that class. Right. Otherwise, we will move ahead and then, yeah, so you guys will miss that. Because what I want is that before your school reopens, we complete the syllabus as well as the revision, so that yeah, everything is clear to us. Noted, guys. So this is on Saturday. And whenever you guys have noted it down, so please tell.
Done, sir.
Done. Aisha and Saad, what about you guys?
Done, sir.
Yes. So now only few things are there. Okay. So what is left? Okay. So magnetic force and Lorentz force. So this is left, right, and then moving coil galvanometer. So this is right, and in this we have also force between parallel wires. Okay, so we will talk about it. So on Saturday, I will talk about it. And then on Tuesday, I guess this would be completed. So I guess in 3 classes, you would complete this chapter. So please come on Saturday, okay, guys? And yeah, go into the log into your Learnivio account, go into the class assessment, and then you will find the active test. So please take that test. I will ask the Learnivio team to make waiting, right? And you guys please join that waiting. Aisha, Mariam, and Saad. So you guys please join that waiting. Okay, on Saturday. Yeah, did you guys find the active test? Mariam, Aisha, and Saad.
Yes, sir.
Good, good. All the best, and yeah, complete the test, and then you guys can. So why isn't it waiting?
Hello.
Yes, yes, Rifa. Assalamu alaikum.
Walaikum salam.
Yeah.
Yeah. Can you start the class early? Because I have to leave early. That's why I joined early.
Oh, so that is why you joined 15 minutes early. So when do you want to leave?
8:30
8:30. Okay. So
or yeah, 8:30.
Riva, to tell you bluntly, you have missed so many classes, right? And we are very far behind of our syllabus. Uh,
Yeah, actually, when
okay.
I told her to keep the class at 7:30, but
Oh,
she said that she cannot do that. So
yeah, because we have this class, right? So uh, we have classes. That's why we cannot arrange classes. Okay. So
is it possible to keep the class at 4 o'clock or 5 at least?
4 is 6:30. So you see that at 6:30 I have this class, right, which I am taking currently. So yeah.
Because 8 o'clock is a bit late and everything. It's a peak time for me.
Okay, okay. So we'll talk about the timing, right? Yeah. So we'll talk about the timing later. So let's see what we can. And Aisha, Mariam, and Saad, you guys, please join that other meeting. Okay. Yeah. Okay. So yeah, let us start. Yes, Saad, please join that meeting. Okay.
Just excuse me only this month because my holidays are there right now, so that's why
Oh,
it's happening.
yeah, because the Learnivio team is asking me to complete the syllabus and right. So you see,
Yeah, okay.
yeah. Okay. So now, yeah, let's quickly start, right? And we completed the elimination method, right? So now you said that you want to start the coordinate A
I
coordinate.
I did the homework also. I
Oh,
sent.
you have also completed. So